Hello and welcome to another lecture of ECE 105. So in today's lecture we're going to talk about these RCL circuits, and hopefully this will be a pretty short lecture because we've already actually done all of the hard work to understand what's happening here. All we really need to do is kind of figure out how we get a differential equation to model what's happening in this particular circuit, and then set up some equations, and then we could just argue, hey, in the last couple of lectures, we did all the work to figure out what can happen in all these various cases. Nothing really changes here, so we can jump to do an example and call it good. Okay, so what is the RCL circuit? Okay, so here I have a pretty simple circuit. I have some type of battery or generator, some type of power source sitting here. Then I have this plus here indicating that the circuit, or that the electricity is flowing in this direction. Okay, so it flows past a resistor, R, and then it flows past this induction coil, so that's my L, because we call the inductance by this symbol L here. And then we finally go past a capacitor, which we denote by C, so RLC circuit. I think I was saying RCL earlier, but RLC. Okay, so how do we go about trying to get a, say, equation to model circuits like this? Well, if you recall way back in the day when you say we're doing Math 115, you dealt with circuits where you had these resistors and some battery sources and nothing else really going on. And in that case, you ended up with a simple algebraic system of equations that you needed to solve to find out what's happening. Well, here it turns out that this induction coil and this capacitor here don't have nice algebraic expressions for what's happening, but they have differential expressions in terms of what's happening. Okay, so in general, we can describe the current flow via derivatives as it goes across here and here. So let's examine what's happening in details here. Just like with Math 115, we need kind of a governing rule of physics to try to get an equation to model this circuit. And here, what we're going to end up using is Kirchhoffs' law. Okay, so again, this is very similar to what we've seen with Math 115 because it's the same Kirchhoffs' law. Generally speaking, Kirchhoffs' law simply says that the sum of the voltage drops as I go across each one of these terms here is equal to the voltage that I'm kind of inducing by this battery here. So just stealing the terminology that, as it's written in the book, Kirchhoffs' law, this is simply the statement that the sum of the voltages drops given by this resistor coil or induction coil and capacitor is simply equal to the impressed voltage, which is just a way of saying the voltage that I'm coming out of this battery here. Okay, so let's kind of chase out these details by just kind of telling you what happens to figure out what happens with each one of these type of elements of the circuit here. Okay, so what is the voltage drop when I go past the resistor? Well, in order to talk about the voltage drop when I go across the resistor, I need to introduce the idea of the current. And the current is just the flow that's going across here. So what I simply do is I really define this thing I, and I is representing the current as I go across here. Okay, so with this new variable I, we know from Math 115 that the voltage drop, so voltage drop due to this resistor here, is simply equal to the resistance of the resistor R, which is generally given to us in ohms, multiplied by the current, which is generally given to us in amperes. Okay, so here we just simply get VR is R times I. Okay, and this, if all of these two other terms here were resistors as well, that would just give me a system of algebraic equations. Well, in this case, one simple algebraic equation because there's only one loop here, right? More loops would give me more equations. Okay, so now what happens at this induction coil? So we didn't cover this in Math 115 at all. You might have seen it in circuits, but I'm not really going to explain the details here. But it turns out that when you go past an induction coil in the opposite direction of here, so go from positive to the negative side, then the voltage drop is going to simply be equal to, well, we'll call it VI for induction coil, this is equal to L, the inductance of the coil, multiplied by not I, but the derivative of I with respect to time. Okay? So here, since I have a derivative popping up here, when I go to apply Kirchhoffs' law and add these together, I'm going to get a differential equation. Okay, finally, the capacitor. How do I determine what's happening here? Well, with the capacitor, two things are going on, right? So the capacitor has the ability to store a certain amount of energy, given that flow is going in the correct direction, all that good stuff. So when flow goes across it, the capacitor will absorb some of that energy in terms of a charge. So how does the charge of the capacitor change? Well, if Q is the charge, then once I turn on this current, or once I turn on the circuit by closing the switch over here, the change in capacity will simply be given by the original capacity, say at some fixed element of time that I'm going to call t is equal to 0, plus the total sum of the amounts of energies that get absorbed by this capacitor from time equals to 0 up to t. Okay, so what's the energy that gets absorbed by the capacitor? Well, it turns out that for any infinitesimal element of time t, I simply have that the current that gets absorbed is given by this I. So here I could just do I of tau d tau. And here I'm using tau as a dummy variable, but really I'm integrating with respect to time here. Okay, so that tells me how the charge of the capacitor goes up, but that doesn't tell me how the voltage drops. Well, it turns out that the voltage drops based off of the charge. So the voltage drop due to the capacitor is simply equal to how charged the capacitor is divided by the total capacity of it. So for the capacitor, I get these two separate equations here that model what's happening here. One of these tells me the voltage drop itself, and the other one gives me how to compute the charge here. Okay, so now if I put all of this together, if I apply Kirchhoffs' law, what happens? Well, I would get that the sum of this Ri plus this term plus this voltage drop is simply equal to whatever energy is coming from the battery, given that the switch is closed. So Kirchhoffs' law will simply give me, if I put this together, my V sub R plus my V sub I plus my V sub C is equal to my E of T, which I'm going to refer to as E of T here. Okay, so if I simplify this out, this gives me an equation that's not kind of my standard differential equation that I've seen before, but it can ultimately be kind of manipulated to be put into that form. Okay, so here, just to be formal, here I have my I prime, but here, this V sub C is where the problem happens. This is Q divided by C. So now here I have two independent variables, right? So here, just note that we have two independent variables in this case. So to be explicit, we don't know what I is as a function of time. So I is unknown. And we don't know what Q is as a function of time. And it turns out that the equation for I, if I call this thing here the equation for I, depends on Q, and the equation up here that we had for Q depends on I. So this equation, along with this equation over here, which I'll just write out, these equations are coupled. So if I put this together, the system that I need to solve is simply this top equation with this bottom equation. So just putting that in words here. Okay, and how do we go about solving a coupled system of equations? Well, in general, you could try to solve one, but then you still have that Q variable floating around. So you can't really solve one of these on their own. You really either need to do what's called decoupling them to get a single equation involving either I or Q, solve it and plug it into the other one, or you need to do something fancy with some type of transform that allows you to do all of this at once. So here what we are going to do is called decoupling, and we're going to decouple this system to get a single equation with respect to Q. Okay, so why Q? Well, it turns out that it's easier to just decouple to get an equation for Q rather than trying to get an equation for I. And in general, that's not always going to be the case. You just kind of have to look at it and guess of which one is going to be the easier way to go about doing it. So what can I do here? Well, I know Q is some constant that I don't know. Well, you could measure it, right? Plus this integral of I, right? So if I want to get an equation just for Q, I really have two options. I could try to solve this for I in terms of Q, plug it in here, and then get an equation for Q. That's not going to be the good way of going about doing it because the hard part is solving 1, not really evaluating this integral 2. Well, depends on what I is as a function. On the other hand, what I could do is here, if I wanted to solve this thing for I, or if I could solve it for I, then I could plug it into this top equation 1 and I would be done. So I can't really solve this for I as it stands because I have this integral of I, but I can get rid of the integral. How can I do that? Well, I can compute the derivative with respect to time of equation 2. Okay, so if I do this, what happens? Well, here I'm going to get Q prime. Q naught, that's a constant, so nothing there changes. And here the integral of the derivative, well, since my lower bound is 0 and my upper bound is t, fundamental theorem of calculus just gives me that this will simply be I of t. Okay, so from here, I now have that I is just Q prime. So now if I put this in 1, so using this in 1, what do I get? Well, from here, I replace all the i's with a q prime. So here I'll get L q prime prime plus R q prime plus 1 over CQ is equal to this forcing term E of t. Okay, this is a differential equation for Q that we know how to solve, right? So L, R, and the capacity, we can assume those are constant, and generally speaking, they will be unless you have some kind of more complex things happening up here that would cause this to have a variable resistance, a variable inductance, or a variable capacity, but generally speaking, we can make this assumption, at least for simple circuits. And now what I can do is I can solve this equation here. Okay, so our decoupled system is thus well, we have our equation for Q, so we'll call it the Q equation, and that is just this term here. And we have the equation for I. So explicitly, our I equation is simply going to be this equation that I found here when I integrated this thing to find I. Okay, so now what I can do is I can solve the Q equation using the techniques that we've done previously, and then after we do that, we can then differentiate for Q to find what I needs to be. Okay, so yeah, if we want to know how the charge of the capacitor goes, we just do that, and then based off the charge of the capacitor, we can find the throughout the circuit. Okay, so here I want to make a comment on this table 6.3.9 in the text. So I'll just paste it here real quick. So this table compares what we had for the spring case versus what we had for the electrical case. Okay, so in the spring case, we wanted to solve for the displacement y, and the velocity of the displacement was this y prime. Here, our displacements, the kind of analog of it, will simply be this charge q, because it is kind of the differential equation here matches what we had previously for springs. And since the derivative of q is the current is our analog of velocity. Previously, we had external forcing factors where you could push or pull on the spring or pendulum or swing or whatever. We called that f of t. Now we have this impressed voltage due to the battery of E of t. Before, we had this mass m that was multiplied by the acceleration term, this q prime prime. Now we have this inductance, L, that's being multiplied by the second derivative of charge. So that's kind of our mass type term, if you will. And then we had some dampening, which is previously was called the C, and that was the term that was multiplied by y prime. Now we have this resistance, which takes the kind of functional form of this dampening that we've seen before. And finally, we had this spring constant that evidently is spelled with a C, K, that we had multiplied by this y term here, and that represented the amount of force that was caused by the stretching of the string beyond its kind of resting point. And now we have the capacitance 1 over C instead. Okay, so there's this perfect analog between this RCL circuit and the spring that we saw before, or if you want, you could think of the spring as a pendulum or many other things. Okay, so there are a ton of applications where you get these type of analogs. For instance, if you want to talk about the electrons, at least in the classical sense, orbiting around a standard atom, say like a hydrogen atom, you can get a very similar analog to this here. Okay, so all the things that we had previously with the spring problem, when we analyzed all those cases, still hold here. So let's just briefly mention this for a kind of completion. Okay, we're not going to drive this. You could, but you've already drove this, so it's not particularly interesting to do this. So in the case where E is 0, you can have a bunch of different cases. So in this case, we're going to get a bunch of free oscillations, and it turns out that you can have 3 different cases that can happen here. Okay, so this can either be underdamped, and again, this is the case where we just keep getting those oscillations occurring, where you kind of overshoot and just kind of go back and forth due to that exponential factor. And then we have 2 types of dampening that you can get, where you don't get those oscillations occurring, one of them being overdamped and one being critically damped. And again, these here correspond to the bit where the roots are real and where we have 2 real roots that have the same value. Okay, so in both of these cases, the same analysis that we had before holds for Q. Okay, so given Q, we just take its derivative to get I. So if Q has these kind of oscillatory or non-oscillatory features, then I will maintain some of those features. Just you're taking a derivative, right? So there's going to be some similarity between the 2 functions. Okay, so in addition to this, we can also examine the case where we have no forcing. So in this case where we have E of t is not equal to 0. Okay, so in this case, we have an analog of theorem 6.2.1 that happens here. Not going to go through the details. Yeah, it really depends on what type of forcing term that happens. But you could have things that grow unboundedly. You could have things that couldn't. But given that it's sufficiently nice, the amplitudes will still be bounded here. And really there to kind of define sufficiently nice, we need Fourier series. We will talk about that later. Like in terms of Fourier series, we probably won't come back to this particular question. Okay, so here, since we've already done all of this kind of hard work, let's end this lecture and make it a pretty short one, especially nice since we have 4 lectures this week. But let's just simply go through an example from the text. Okay, so here we're asked to find the amplitude phase form of the steady state current of the RCL circuit in the previous figure if the impressed voltage provided by an alternating current generator is given by this term here. Okay, so what do we mean by this steady state current? Well, it turns out that like in the work that we did in the previous lecture where we had this E of t is non-zero, but was something that was of this functional form here, of this cosine of omega t factor here, the effects of the initial conditions die out as time goes off to infinity because those modes have a decaying exponential attached to them, right? And the decaying factor purely comes from the fact that we have this resistance here. So the initial data eventually doesn't matter, and in the limit as t goes to infinity, the only thing that really matters is the relative balance of this forcing term here that we have, and the terms here for the inductance and for the capacitor here. And really, in some sense, you would expect the capacitor term to go away once the capacitor is full, right? So what we want to do in this case is we simply want to try to solve this differential equation here for Q, given this particular forcing form for that E sub t. And then after we do this, we want to write it in the phase form that we want to write it as. And then finally, we want to use the second equation to find out what the current is, which is what we really care about, okay? So here we don't care about the solutions to the homogeneous problem purely because they will decay exponentially in time, and in the limit, that goes away. Okay, so what I am going to do here to kind of save time, and since it's kind of nicely written in the text, is to just regurgitate the solution here and go through the key facts that are kind of important. So like TLDR, why do we care about what the book did, and what are the things that you might get stuck on? Okay, so here, this is the equation that we want to solve for Q, right? So if we can solve this for Q, then we can find I, and we're good. So really all we've done is we put in the functional form for our E of t into here. Okay, so now instead of solving this from scratch, which you could do, and we could ask you to do it from scratch, but we've done a lot of hard work already to solve the spring problem from scratch. So why rehash all of this stuff, right? You might need to do it if I ask you to rehash something on an assignment, but I won't ask you to rehash something like this from scratch on a test. So yeah, you can kind of use for this material that we've worked hard to obtain for granted there. But yeah, why work harder when we don't have to? Okay, so here, given this thing, we know what the solutions look like. In particular, okay, so here was the solution that we found before. Okay, so now if I want to go from this solution that I found before to a solution for here, all I need to do is a simple transform. Okay, so here just by kind of noting between this and this, if I let M equal L, if I let C equal R, and I let K equal 1 over capital C, okay, so capital C, little c, I'll put a tilde over this one, and nope, yeah, I'll just leave it like that. And if I let my forcing term F naught be equal to E naught, so if I do all of this, then all I have to do to get a solution to this thing here is to plug in this here. So that's exactly what the text is doing here, okay? So here I replace the F naught with the E naught to get this term here, K with 1 over C. Oh, I have an M, replace it with L. I have a C squared, replace it with R, etc. Okay, pretty straightforward. So after I do that from here, this is my solution to my differential equation that I have, or that I want to solve. And from here, if I want to actually compute the steady state and all that good stuff, or steady state current, what I need to do is differentiate Q, which is readily done, and then that's going to be my steady state current. And again, this will be my steady state current because no matter what the initial conditions are here, when I solve the homogeneous equation and get those arbitrary, well, not arbitrary, but those particular functions, those will decay exponentially in time to 0. So no matter what initial condition I have, those the impact of those again goes to 0. Okay, so let's end this lecture by giving you some assigned reading and some sample practice problems, and of course your meme. Okay, so I want you to read section 6.3, and for practice, I want you to look at examples 1 through 10 on page 295. Okay, so these are just solving particular circuits here, and I'll probably either give you a circuit or a spring problem on the next homework. Probably, I'm leaning towards circuit, but yeah, both of the type of applications are pretty straightforward. It's just figuring out what numbers go where and then plugging it in. So for our meme, we have circuit goes in, current goes out. I can explain that. Okay, so yep, that's everything for this lecture. Nice and short in comparison to the other lectures, and that's entirely because this was a pretty straightforward application. In the next lectures, we're going to examine the Laplace transform, so those lectures again will unfortunately have to be a little bit on the longer side to cover everything that we need to cover there. But I have a little bit of wiggle room, so I'll spread them out a little bit. And yeah, so at the end of lecture 16, just for those of you kind of looking ahead, that will be the end of the material that could be on the midterm. Okay, so I will talk to you later and see ya.